couple of announcements really quick. So first of all, here's a question that I have. Would you prefer our session to be over Zoom, or would you prefer in person? You want in person? Okay, so it'll be Sunday at 6, and I will be recording on Zoom for anybody who wants it, or if you want to go back and take a look at what I said, that's fine. Here's a really quick note for you that just to kind of file away. So in your study guide, there is a question about expertise. So I went and I looked through our exam and I did not put an expertise question on it. So here's what I'm going to do. Probably sometime on Monday afternoon, I will record a section on expertise for those who want it for your own enrichment. But for the purposes of today, I'm going to go ahead and move on to judgment. Decision making, I have previously recorded, and I will share that with you as well, because we do have a couple of decision making questions, and I'll try to be mindful of specific time points. So I'll highlight certain time points that I want you to kind of look at in the video to help you answer questions. So one other thing that I will kind of mention, since we're kind of moving away from expertise and problem solving, is that I hope you're kind of looking at McRaney as well, because there is going to be a question on the Dunning-Kruger effect. Now, is anybody here already familiar with the Dunning-Kruger effect, or have you heard of it before? Okay, so the Dunning-Kruger effect is basically kind of the idea. How many of you had this happen after you took general psychology or intro psych? You were basically like, I understand everything about psychology now. How many of you kind of felt that? So here's something kind of interesting that we know. When you get a little bit of knowledge in something, or you're a little bit talented in something, but you don't have a lot of good feedback about what you know and what you don't, you often tend to be overconfident in your abilities. What's really interesting is that with the more knowledge that you get, one of the things you're going to find is that you don't know what you don't know. You know what you don't know. When you get more expertise, you kind of have an understanding of what you know and what you don't. So I can stand here and I can tell you I'm a short-term memory expert. I also know a lot about things like attention and neuroimaging, and to a lesser extent, EEG. However, when it comes to other topics in cognition, things like problem solving, judgment, and decision making, I know those less well, but I probably know them better than somebody who is like a clinical psychologist or a social psychologist. Now, on the other hand, somebody that has just a little bit of knowledge, they're going to think they're better than they are. So one of the things that we find is that when you get a little bit of knowledge, but not enough to make you an expert, you don't know what you don't know. So how many of you used to watch American Idol auditions? And how many of you have watched the American Idol auditions and been like, why did that person try to audition for this? Why did they think they were good? Now, in some cases, it's just because they want to get on TV. In other cases, if you're okay, I can be in key, but I'm not a great singer. I can sing on key, but I'm not really great with my voice or anything like that. That might lead me to believe, especially if I'm the best in my family, I don't really know what I don't know. And so that might lead me to think I'm more talented than I actually am, because I haven't gotten the opportunity to really develop that expertise or get good feedback. So that's kind of what the Dunning-Kruger effect is. Does that kind of make sense for everybody? Okay. All right, so make sure that you know that. If I don't record a video for you, I will link you to a video that I recorded for Cognitive Psych when it was hybrid, so that you have information on expert performance if you want it. because if we don't have an opportunity to talk about it, I feel like I should at least share what I know with you, even if we don't test on it. But for right now, I really want to focus on the test. So we're going to go ahead and talk about judgment, and you should have these notes, and I may have given them to you in full, I think. Merry Christmas. Merry Christmas. All right, so we're going to talk about judgment, and whatever we don't have time for, I will give a link to a video for you to watch, and I will kind of mark important time points. All right, are you ready? We're going to start with some math problems. Ew. But don't worry, it'll be okay. So we're going to start by talking about judgment and decision making. And so one of the things that I think you will really like about this chapter and this section is that judgment and decision making in general are very easy concepts to understand. And a lot of these findings have a lot of applicability to your everyday life and your situations. Additionally, a lot of people who do research in judgment and decision making, a lot of them actually, we have quite a few cognitive psychologists who have actually gotten the Nobel Prize. They usually get it in economics and usually for judgment and decision making. And that's because a lot of what we find here can be applied to economic and financial decisions. So what is judgment? Judgment is basically drawing inferences about situations or different types of events. So how likely is this to happen? Or how representative is this person compared to people around them? So the goal of judgment is accuracy. We want to make accurate judgments of situations. So yesterday it was supposed to rain and the temperature was supposed to drop at some point, but it kept kind of shifting. And so you have to ask yourself, is it a good day to bring an umbrella? How likely is rain today? And how likely is it that the temperature will be different when I come in compared to when I leave? And that might, those kind of judgments ultimately affect the decisions that you make. So decision making is when we are choosing between various options, and the outcome of decision making is consequences. So ideally, when we are making decisions, we want good consequences. I hope you have a wonderful weekend to look forward to. I am working the murder mystery again tonight for prospective students. And then I get to go to Kansas City and buy treats from Trader Joe's and do Christmas shopping. And because it's so cold, I may buy myself another coat. It never hurts to have more on hand. I like having options, huh? You'll get, well, so yesterday it was 70 degrees. It's kind of hard to acclimate to that. There's probably going to be some points in February where you really wish we had this weather. You'll acclimate to it, or be like me and bundle up. I always prefer to feel comfortable, even if I look ridiculous while doing it.
Is that the jacket you were talking about the other day?
Yeah, it kind of looks like a robe, doesn't it? It's a little too big, but I thought I wear bulky sweaters. I need to give myself space. Plus, I think oversized is a little bit the style right now. I like it occasionally, but then people laugh at me when I wear it, and I'm just like, meh. Yeah.
How does it get in the rain?
I don't know. It's acrylic, so thankfully I haven't had to put that to the test.
That looks like a bad wet.
If it's raining, I would wear my puffy coat because that's a little more water resistant. Okay. So we're going to talk about judgment research right now. So we're going to start with a pretty straightforward problem, and it's going to end with math. Don't worry, you don't have to know about math to do well in this section. No math is required. I'm just going to explain the math for you. Okay. So what you are looking at here is a really scary formula. So what we find is that when we get information, one of the things that we find is new information can change how we judge a situation. And so one of the things that we have to focus on is something called Bayes' theorem, which is right here. The formula is right here for you. So basically, what this is saying is that if you want to judge whether something is likely or not, you need to look at the base rate of occurrence. You need to see how common it is already to be able to make a judgment of how likely something is. So what you're looking at here, and this is a little scary. So this is the probability of hypothesis A, given the data that you have, over the probability of a different hypothesis, hypothesis B, given the data. So maybe hypothesis A is it will rain today. Hypothesis B is it will not rain today. So we need to look and see what the prior rates of occurrence are for rain on November 11th. And then we can make a better judgment call. So what we do to figure out this is we have to multiply the odds of each hypothesis being correct. And then we do something kind of interesting. This is the probability of the data being possible under hypothesis A and the probability of the data being possible under hypothesis B. So what you're looking at here, these are the prior odds of each hypothesis being correct before you collected the data, and then you're going to multiply that based on likelihood. This is the probability that the data are likely under hypothesis A being true, and the likelihood of the data given that hypothesis B is true. So this is a scary formula. I will not ask you to know this, but what it's telling you is if you want to make a good judgment call for what you should do today, you should look at the data of prior rates of occurrence. If you want to make a pretty good call over whether or not you should wear a coat, one of the things that you might want to do is look at some prior data beforehand. What is the average temperature for November 11th? For example, 3 years ago, it was 22 degrees and snowing outside. Yeah, I did not like that day. This is better in comparison because at least we have sun. Vitamin D is good for you, y'all. So the idea is that if you want to figure out how likely something is, you can't just judge in a vacuum. You need to look at the prior rate of occurrence. So I'll kind of get to what this means in our next example. So I'm going to have a word problem for you. You don't need to write anything down, but we're going to talk about it a little bit. All right, everybody good? Anybody need some more time? So here is an example. So this is where Bayes' theorem really comes into play. So a taxi cab was involved in a hit and run accident one night. Of the taxi cabs in the city, 85% belong to the green company, 15% belong to the blue company. An eyewitness identified the cab in the hit and run as being part of a cab from the blue company. However, when they tested the eyewitness's accuracy, they were wrong about 20% of the time in appropriate visibility. So my question is, what is the probability that the cab is blue? Does anybody have an answer? Anybody have a guess? You can use math, but you can also just tell me what you think in general. Yeah, Ashton.
Low probability,
You think it's a low probability that it's blue? Why?
because it's, if only 15% belong to the blue company and 20% of that person's memory is wrong,
Mhm.
then it's likely that it wasn't blue.
Okay. Does anybody agree with Ashton that the odds of it actually being blue are not very likely? Okay. Is there anybody that thinks that there is a high probability that it's blue? Okay. And how many of you don't know and you just want to get the answer? Yeah, Sarah? You want the answer? Well, so one of the first things that I will mention, good job, Ashton, you were actually thinking like a Bayesian. And here's why. Most people, when they get this problem, they only focus on the fact that there's eyewitness identification. So a lot of people, their first instinct will be to say that there's an 80% probability that it's blue because the eyewitness identified it as such, and they're only wrong 20% of the time. So some people immediately jump to that 80. However, there is some inaccuracy here, and in general, less than 1 in 5 cabs that you see are going to be from the blue company. So you have to pay attention to those base rates of occurrence to be able to judge the likelihood. Now, if you want to see how this works in the formula, here's what we do. The odds ratio is 12/17. So this is basically plugging in Bayes' theorem. So here are the original probabilities. So basically 15% of the cabs come from the blue company, 85% come from the green company. And then we have the probability of our data, given that the hypothesis A is true. If it is a blue cab, so we have identification, given the data, this is 80%. And then there's the 20% inaccuracy. When you multiply these together, you get 0.12 over 0.17. So this is, for those of you that don't know, what we have right here is what is called an odds ratio. You do not have to know this for this class. I did not learn about what an odds ratio was until my first year of grad school. But to kind of show you a little bit about how we calculate an odds ratio, so what we're going to do here is we're basically going to take, so we have 12/17. So this is for blue, this is for green, and we're going to take that total. So it's basically 12 over 12 plus 17. Which equals 12/29. And when we do that, there is a 41% probability that the cab is blue. On the other hand, for the green cab, we do 17/12 plus 17. So that equals 17/29. So that basically makes it a 59% probability. Now, they're pretty close to each other in those cases. And that's because while there are more green cabs, we also have that eyewitness identification, which is pretty accurate. 80% is not bad. So because of that, it kind of moves blue a little closer to green. But most of us are not going to be able to calculate those fancy pants odds ratios. And to be completely honest, I'm not always going to do that either. So one of the things that is helpful to pay attention to here is that base rate of occurrence. So the fact of the matter is more cabs are green than are blue. As a result, odds are pretty good that that cab is actually a green cab. So why do so many of us get this wrong? Well, first of all, it's pretty mathy, and most of us see a math problem and go, peace, I'm out. You're like, I don't want to do this. So we often don't take prior odds into account. So those of us who aren't scared off by the math don't focus on the prior odds. So when we do this, when we pay attention to the prior odds of occurrence, we are looking at what is called base rate information. This is the relative frequency of an event or an attribute. So in general, if I had to make a guess of what the most common eye color is of people in this room, I would have to guess that the correct answer is brown. Why? Because in general, most people's eye colors are brown. Now, it may not be correct in this particular instance, But in general, it's a pretty good rule of thumb to have just based on the base rates of occurrence. In our cab example, green cabs are way more common, and thus they're going to be more likely to be involved in a hit and run in general, just because of the sheer number of them. But we focus in on that eyewitness information and assume that it must be correct without taking the base rate into account. We're going to do a lot of problems like this. And I'm thirsty again, and I'm out of soda. So we have a backup plan, but I'm almost out of it too. Maybe a third. I'll be all right. Everybody good here, or does anybody need more time? Okay. So don't write the problem down. Just kind of work with me here. So Jack is 45 years old. He's married with 4 children. He is generally conservative, careful, and ambitious. He shows no interest in political or social interests or social issues and spends most of his free time on his many hobbies. These include carpentry, sailing, and numerical puzzles. So, what is the probability that Jack is a lawyer versus the probability that Jack is an engineer? Now, your first instinct is to say, Dr. Gilchrist, you can't possibly expect me to judge somebody's career from a personality profile. So yes, technically that is the correct answer, but I'm not giving you a choice here. What is the likelihood that he is a lawyer versus an engineer? Ashton, what do you think?
It's more likely that he's an engineer because he shows no interest in political or social issues.
Okay.
And because his hobbies are pretty building and numerical based, which tends to fall under engineering.
Okay. How many of you would agree with Ashton? Is there anybody that disagrees with Ashton? Okay. So once again, this is probably an instance where we need the base rates of occurrence, right? If there are more lawyers in the world than engineers, odds are pretty good that it doesn't matter what Jack's personality profile is. He's probably a lawyer just because there are more lawyers. On the other hand, if we picked engineer versus somebody in retail, he's definitely more likely to be in retail. There are way more people in retail than in engineering. But we decide that Jack's personality fits a prototype that we have in our mind of what an engineer is. Like, lawyers don't like to do puzzles. Lawyers aren't interested in political issues. Like, lawyers are interested in political issues. There's no way he could be a lawyer. So we kind of get this personality profile going. And because he fits the profile, we assume he's an engineer over a lawyer. Is that what most of you kind of went with? There's no shame in it. We all do it. This is what is known as is known as the representativeness heuristic. Jack fits a prototype. Now, some participants were originally told that Jack's description was selected from one of 100 descriptions, not prescriptions. So 50% of people were told that there were 70 lawyers in this description and 30 engineers. So what should people pick in that instance? He's a lawyer, base rate. On the other hand, the other 50% were told that 70 of them were engineers and 30 were lawyers. In that case, they should pick engineer because there are just more of them. But regardless of what condition participants found themselves in, most people said that there was a 0.9 probability, so that's 9 out of 10 probability, that Jack was an engineer. We ignore base rates and we focus on how well somebody fits a prototype. This is known as the representativeness heuristic. I I am very much looking forward to Trader Joe's this weekend because they have a plant-based Thanksgiving roast that is stuffed with cranberries and it comes with really good gravy and it's breaded. I'm gonna get like 2 because I make sandwiches out of them. Your lipstick is very blue. Is it because you're cold?
No, I didn't.
You went out in the cold and your lipstick turned blue because you're freezing. It seems appropriate for today.
Oh yeah, I didn't go outside until after I did my makeup and my fitbits.
Wouldn't be so bad if not for that wind. I will say that much. All right, everybody good here? Does anybody need some more time? Yeah, I see pens wiggling. I can wait. All right. Everybody almost done? Okay. So with heuristic, so when it comes to judgment, we already kind of talked about using heuristics, these simple rules of thumb like means end analysis and hill climbing to solve problems, but we also use heuristics to make judgments. And this was largely explored by Dan Kahneman and Amos Tversky, and they actually won the Nobel Prize in economics for their efforts in this area. So a heuristic, just to remind you, is a general rule of thumb. It is a very simple thinking strategy, and generally it's pretty effective. It will usually get you to a solution, but because it's based on personal experience, it can lead to systematic errors and to biases. So what we just saw in the Jack example is what we call the representativeness heuristic. So we assume that the most typical members of a category are the most frequent. So Jack is more likely to be an engineer because he fits the profile in our mind of what an engineer should be. Additionally, the representativeness heuristic basically says that any event that is similar to most of the others in the population is going to be representative. So for example, I have often been told I don't have the personality profile of a professor. Most people, when they think of a professor, they usually think of somebody who's a bit more introverted. I don't always fit that profile. And that is okay. Why are you sorry? You didn't do anything. You're cold.
No, I didn't realize I put on my sweater backwards.
Oh, you cut off the neck.
Yeah. But I didn't realize I put it on backwards until I was like, why is this touching my neck?
You're starting a trend. Right. Right. Everybody good? Okay. So we're going to try another problem. You're going to like this one. So this is Linda the supposed bank teller. So Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. So I want you to judge the probability that Linda is a bank teller, the probability that Linda is a feminist, and the probability that Linda is a feminist bank teller. So which of those do you think is most likely of those three possibilities? Which one would have the highest probability? Okay, is there anybody here that says the feminist bank teller? Okay, congratulations. Like y'all, like Ashton, you're wrecking all of my demonstrations. Yeah, you, Hannah and Allie are all wrecking my demonstrations because you also said you had the Bayesian thing. So let's talk about what happens when most people get this problem. What do most people pick? They pick the feminist bank teller. So here's the thing about probability. So the probability that Linda is a bank teller is associated with a certain probability. Yes. The probability that Linda is a feminist is associated with its own probability. So here's the sneaky thing about adding two probabilities together. So if we want to judge that Linda is a feminist bank teller, you don't actually add them, you multiply them. Probability is multiplicative, not additive. So if there's a 1/2 probability that Linda is a bank teller and a 1/2 probability that Linda is a feminist, you actually get a 1 out of 4 probability that Linda is a feminist bank teller. So it's kind of like how the probability of a heads up coin is 50%. The probability of a tails coin is 50%. The probability of flipping heads and then tails is 1 out of 4. Because probabilities multiply when you have additional events. So most people will say that Linda is a feminist bank teller when really out of these three options, it is the least likely, not the most likely. But Linda being a feminist bank teller seems a lot more reasonable to us in the moment compared to either other possibility. So this is what's known as the conjunction fallacy. So the conjunction fallacy is basically the belief that a combination of two events is more likely than either one on its own, when that is not actually the case. Oftentimes, when you give people this problem, participants will rate a conjunction of events to be more likely than either one on its own. All right. Everybody good? It's kind of interesting, is it? So something else, I will just kind of share this with you because I think you might find it interesting. Something that's kind of related to this is something called the gambler's fallacy. So I'm going to put this on annotate. So I want you to imagine that we're doing a bunch of coin flips. Which one is more likely? 4 heads in a row, or wait, which is more likely? Heads, 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 or heads, tails, heads, tails? They're equal. They're equal. So again, probabilities multiply. Heads, so 4 heads in a row is basically 5.5 times 4. So if we do that, that is basically, so actually, no, I don't think it's even that. So it's 1 divided by 2 equals, so 0.5 times 4. Yeah, I'm like, wait, no, that comes to 2. That's not right. So 0.5 times 0.5 times 0.5 times 0.5 is actually 0.0625. So you basically have 6.25% of getting this particular sequence. But guess what? Every coin flip is independent from the one that came before. As a result, most people will say that this one is more likely because it seems more realistic, when the truth of the matter is the probability of getting tails is the same probability as getting heads. As a result, 4 head flips equals the probability of 1 head, 1 tail, 1 head, 1 tail. And that is the gambler's fallacy. And now you can challenge all of your friends. You can trick your friends. Don't trick your friends. Okay. So another heuristic that we often will kind of focus on is something called the availability heuristic. So the availability heuristic is basically you judging the frequency of an event based on how readily it pops into your mind. So if I ask most people, what is the more common cause of death? Is it murder, or this is going to be on YouTube, so unaliving yourself? Which of these would be more likely? Raise your hand if it's the first option. Raise your hand if it's the second option. Y'all are really good at busting all of the, like, you are very smart cookies. You don't fall for my tricks. Most people will tell you that they think that murder is the more common cause of death compared to unaliving yourself. And the reason for that is because generally murders get a lot of press. Murders get a lot of press. The latter instances usually do not, unless they are somebody very famous. And also because our society very much has a big taboo about those things. So we'll think that one is more common than it actually is, simply because it gets more press and we can think of more instances in our mind. Now, here's a more mundane example. Is there anybody here who's afraid of flying? No, everybody is cool with flying?
Never been on one.
Okay, but would you be nervous to go? Okay, can I ask you a question? Are you a little worried about plane crashes?
No.
Okay, is there anybody here that's worried about plane crashes? Y'all are braver than me. I hate flying. I hate turbulence. But oftentimes, occasionally, you will find somebody who's afraid to get on a plane because they're worried it's going to crash. And usually what I follow up with is, do you get in a car? And they're like, yeah, I drive every day. And I'm like, you realize, right, that getting into a car accident is far more likely than you getting in a plane crash. But guess what? Most car accidents don't make news. Plane crashes make news when they happen because they are so rare. And because we see them in the news, we think that they're more common than they actually are. If you come to Florida and go to the beaches, you might be terrified of a shark attack because you'll hear stories about them over the summer. But the truth of the matter is, folks, I'm not saying I get in the water, but I grew up in Florida beaches, never saw a shark. Did see some dolphins hanging out in the river, though. That was cute. So the availability heuristic is basically because something pops into our mind more easily, because it's more available to us, we often tend to think it's more common than it actually is. Hertwig and colleagues back in 2005 actually suggested that the reason that this happens is for 2 different things. So one of the reasons that this happens is something called availability by recall. So if you can remember a lot of instances from memory that have happened, you're going to think it's more common than it is. Something else that happens is what is called fluency. Even if you don't have like a whole list of instances, like this plane crash happened and this plane crash happened and this plane crash happened, you might have a sense of fluency where it's easy to bring relevant instances into your mind. And thus, again, you're going to think it's more common than it actually is. I know. How was lunch today? What was it?
Chocolate tomato soup and grilled cheese.
Oh,
My favorite food. Waffle rolls.
I should have gone. Oh, well. Okay, everybody good? Anybody needs some more time? Okay. So here's the thing though, the availability heuristic doesn't always work. So here's my question to you. What's last name is more common in the United States? Bush or Stevenson? Who says Bush? Who says Stevenson? Cool, you're like most people. Now, some people, very few though, will probably say that Bush is more common. Why? We've had 2 President Bushes and we've had a presidential candidate who is also my governor. So Bush is a pretty common name, is a name that you know because it's famous. So it pops up more and it's readily available in your mind. Do you know any person right now with the last name Stevenson? I know like one. So here's what's interesting though. You think that because Bush is in the last name Bush is in the media and is in our history, that it would be judged as being more common. But it turns out that Oppenheimer found in 2004 that participants correctly report that non-famous names are going to be more common than last names that are famous. So one of the things that we do know is that sometimes familiarity is not due to frequency. It's due to the fact that people are famous. And because of that, we can actually overcorrect. So under certain circumstances, we don't always use the availability heuristic. All right. Anybody needs some more time? Sarah, do you need some more time? Okay. All right. So another thing that I kind of want to talk about is what is called support theory. So any given event will appear more or less likely depending on the description. So for example, people were asked, what's more likely? The probability that you die on vacation or the probability that you die of a heart attack while on vacation? Here's what's interesting. Now, you probably got a greater probability that you die on vacation than dying in a very explicit way, like a specific way. But it turns out that most people actually are going to judge more explicit events as being more likely. So for example, if you're not feeling well and you kind of want to take a personal day from class, what's probably going to make me believe you more? I feel sick, or I've got the flu. I've got the flu is going to be judged as being more likely than I feel sick. Now, the reason that people have mentioned that more explicit events might be judged as being more likely is because oftentimes when we refer to something explicitly, we are drawing attention to less obvious aspects of the situation. So, for example, the flu can be a lot more debilitating if you just say you're sick. We don't know how bad this is. Like if you say I have a cold, or if you just say I'm sick, that could be a variety of different things and it's not so obvious. It's not as obvious. Additionally, we have memory limitations. Being more explicit means that we are going to have to process more detail and greater and more specific probabilities than we otherwise would be able to. So a future event often is going to seem more likely when it is supported by extra information. And in general, it's because you and I don't really have the memory we don't have the ability to remember additional information if it's not explicitly stated. So if you say I'm sick, I have to work through the probability that it's a cold, flu, norovirus, COVID, RSV, all of these wild viruses that tend to circulate in dorms in the fall. I know, residence halls, whatever. But I would have to process all of that information. Because you made it explicit, I only have to focus on one thing, and that's going to make me believe that's more common than I'm sick. Similarly, people have actually found this when they do estimates of a terrorist attack. So you get a general event, a terrorist attack in the next 6 months, or you get an explicit event. What is the likelihood that there is a terrorist attack by Al-Qaeda in the next 6 months? What is the probability that there is a terrorist attack that is not by Al-Qaeda in the next 6 months? So if we mention a specific terrorist organization, we actually find that more explicit scenarios yield higher probabilities. Now, again, I mentioned that this could be due to attention issues, memory issues, but the truth of the matter is we don't have as good of an understanding of why or how this works as we could. So we've got more to learn here. And that's always a good thing. Good research should always give you more questions than answers. All right, let me see what's on the next slide. And depending on what happens, well, I will either cover it or I will talk about it in a recording. Yeah, I think we're going to go ahead and stop here. So we have a little bit more to cover with judgment and decision making. So I'm going to give you some links to some videos that you can watch. And I'll kind of give you timestamps of when those can start. And I do believe that some of those older ones are captioned, but I'll have to check if anybody wants captioning for it or anything like that. But be sure to watch those. There are not that many questions on the study guide for judgment and decision making. So I would say try to stick to the things that you know are going to be on the test. Stick to the things you know, and then if you want to go ahead and read through the rest or watch the rest, you are welcome to do so, but I'll try to include some timestamps for areas that I really want you to focus on, okay? Does that sound good? So that way you don't have to watch like 40 minutes and struggle to figure out where it needs to be. Yeah? All right, everybody have a good weekend. Stay warm and enjoy yourself, and I'll see you next